Hey everyone, and welcome to the fascinating world of organic chemistry. You might be wondering what's so special about organic chemistry. Well, it's the study of carbon-containing compounds, which are the building blocks of life itself. From the clothes you wear to the food you eat, organic chemistry is everywhere. Now let's talk about some key terms you'll encounter on your organic chemistry journey. First up, we have functional groups. Think of them like puzzle pieces that give organic molecules their unique properties. For example, the hydroxyl group, OH, is like a friendly neighbor that makes molecules soluble in water. Next, we have isomerism. Isomers are like twins with different personalities, that they have the same molecular formula but different arrangements of atoms leading to distinct chemical behaviors. Pretty cool, right? In a nutshell, organic chemistry is like a giant Lego set where carbon atoms are the building blocks and functional groups are the connectors that create an astonishing array of molecules. So buckle up and get ready to explore the amazing world of organic chemistry. Let's dive into the world of hydrocarbons, the simplest organic compounds made up of only carbon and hydrogen atoms. First, we have alkanes, the nice guys with single bonds. Alkanes are unreactive, like that friend who never wants to do anything exciting. Alkanes are more adventurous with at least one double bond. Finally, arenes have a special benzene ring, giving them unique properties. Understanding these types sets the stage for more complex molecules. Now let's spice things up with halogen compounds. These organic compounds contain halogens like fluorine, chlorine, bromine or iodine attached to carbon atoms. Halogens are like the cool kids of the periodic table, and they bring their own reactivity to the table. The reactivity of halogen compounds mainly revolves around two important reactions: nucleophilic substitution and elimination. In nucleophilic substitution, a nucleophile, which is like a nucleus-loving species, attacks the carbon atom attached to the halogen, kicking the halogen out and taking its place. On the other hand, elimination reactions are like breakups. In these reactions, the halogen atom and a hydrogen atom on an adjacent carbon atom decide to leave the molecule together, forming a double bond between the carbon atoms. Understanding the factors that influence these reactions, such as the type of halogen, the structure of the molecule, and the reaction conditions, is crucial for predicting the products and controlling the outcome of chemical reactions. Get ready to dive into the world of hydroxy compounds, which contain the O functional group, also known as the hydroxyl group. Hydroxy compounds, specifically alcohols, are like the social butterflies of organic chemistry, interacting with various other molecules due to the polar nature of the OH group. Alcohols are classified based on the number of carbon atoms attached to the carbon bearing the OH group. We have primary, secondary, and tertiary alcohols, each with its own reactivity and characteristics. Primary alcohols are like the shy ones, while tertiary alcohols are more outgoing and reactive. Alcohols can undergo a variety of reactions, including dehydration to form alkanes, oxidation to form aldehydes or ketones, and esterification to form esters. These reactions are widely used in various industrial processes, from producing solvents and fuels to synthesizing pharmaceuticals and fragrances. As you explore hydroxy compounds, pay attention to how the position of the OH group and the overall structure of the molecule influence their reactivity and properties. Section 5. Unveiling the chemistry of carbonyl compounds. Let's unravel the captivating chemistry of carbonyl compounds, aldehydes and ketones. These compounds contain the carbonyl group, which is like a magnet for nucleophiles due to its polarity. Aldehydes have the carbonyl group at the end of a carbon chain, while ketones have it somewhere in the middle. Think of aldehydes as the leaders and ketones as the mediators. This difference in position significantly influences their reactivity. Aldehydes and ketones undergo a variety of reactions, including nucleophilic addition, oxidation, and reduction. One of the most important reactions is the addition of Grignard reagents, which act as carbon nucleophiles and can form new carbon-carbon bonds, leading to the synthesis of more complex molecules. Understanding the reactivity of carbonyl compounds is crucial for understanding various biological processes such as carbohydrate metabolism and protein synthesis, so keep those carbonyl groups in mind. Section 6. Carboxylic acids and their intriguing derivatives. Get ready to explore the world of carboxylic acids and their intriguing derivatives. Carboxylic acids are like the mature members of the carbonyl family, possessing a carboxyl group, which is a combination of a carbonyl group and a hydroxyl group. Carboxylic acids are weak acids, meaning they partially ionize in water to release hydrogen ions. They react with bases to form salts and can undergo esterification to form esters, which are often used as fragrances and flavorings. Carboxylic acid derivatives, such as esters, acid chlorides, and amidase, are like the children of carboxylic acids, each with its own unique personality and reactivity. They play vital roles in various biological and industrial processes. Understanding the properties and reactions of carboxylic acids and their derivatives will give you a deeper insight into the chemistry of life and various industrial applications. Section 7. Understanding nitrogen compounds, amines and amides. Prepare to delve into the world of nitrogen compounds, specifically amines and amides. These compounds contain nitrogen atoms, which are like the versatile members of the organic chemistry world, capable of forming various bonds and participating in a wide range of reactions. Amines are derivatives of ammonia, where one or more hydrogen atoms are replaced by alkyl or aryl groups. They are classified as primary, secondary, or tertiary, based on the number of alkyl or aryl groups attached to the nitrogen atom. Amides, on the other hand, are carboxylic acid derivatives, where the O group of the carboxyl group is replaced by an amino group. Amides are less basic than amines and play crucial roles in biological systems, forming the backbone of proteins. Understanding the properties and reactions of amines and amides is essential for understanding the chemistry of amino acids, proteins, and various pharmaceuticals. Section 8. Unlocking the secrets of polymerization. Get ready to unlock the secrets of polymerization, a fascinating process where small molecules called monomers join together to form long chains called polymers. Think of polymers as giant chains made up of repeating units, much like a string of beads. There are two main types of polymerization: addition polymerization and condensation polymerization. Addition polymerization is like joining Lego blocks, where monomers add to one another without losing any atoms. Condensation polymerization, on the other hand, is like building a chain with paper clips, where monomers join together by losing a small molecule, usually water. Polymers are everywhere in our daily lives, from the plastic bottles we use to the clothes we wear. Understanding the different types of polymerization and the factors that influence polymer properties is crucial for designing and developing new materials with specific applications. As you explore the world of polymers, pay attention to the different types of monomers, the reaction conditions, and how they influence the properties of the resulting polymers. Section 9. Mastering the art of organic synthesis. Get ready to master the art of organic synthesis, a creative and strategic process where chemists design and execute a series of reactions to create a target molecule from readily available starting materials. Think of it like building a complex Lego structure from a set of basic bricks. Organic synthesis requires a deep understanding of organic reactions, functional group transformations, and reaction mechanisms. It involves carefully planning a synthetic route, selecting appropriate reagents and reaction conditions, and purifying and characterizing the desired product. One of the key skills in organic synthesis is retrosynthetic analysis, where chemists work backward from the target molecule to identify simpler intermediates and ultimately the starting materials. This process involves breaking down complex molecules into simpler fragments, identifying key bond disconnections, and selecting appropriate reactions to achieve those disconnections. Mastering the art of organic synthesis requires practice, creativity, and a deep understanding of organic chemistry principles. It's like solving a complex puzzle where each step requires careful planning and execution. Section 10. Conclusion. Your journey to conquering organic chemistry. Congratulations. You've journeyed through the fascinating world of organic chemistry. Remember, organic chemistry is like a giant puzzle. Here's a quick revision quiz to test your knowledge. What are the key features of alkanes, alkanes, and arenes? Explain the difference between nucleophilic substitution and elimination reactions. Don't worry if you don't get everything right away. Organic chemistry takes time and practice to master. Review the content, practice problems, and seek help if needed. With dedication, you'll conquer organic chemistry.